的大小跟它绝对有关系，越小越好。但是越小你可能 drop 的时候还稳定。因为你越小的话，到时候你要把这个还是 stop 的话，你就会。
We like to challenge problem 11.
Steady 就是上面跟 steady 的概念就是压力差，高度差距。所以那个 pressure 的基本上压力是很大的。
Please write down your
大接触力越小的话，那个 pressure 越集中，所以然后你的球跟另外的 area 一样，这个受力反而就是第二大非常对应的。因为我们这个然后而且人家工具会更好，因为它可以做些上面的那个时间差，至少会觉得有一个往下的压力，下一个往上压力，它相对的比较差。那你如果说上面是一个圆筒，圆柱筒，然后上面有一个开关，然后就这样。
对，刚才碰接触那边什么是力的，我看到一个。
对啊，这样就可以 screw 说到底是在滑动和是不是有关系等等。所以就说你球拍在什么地方也是非常有关系的。这个不同。对，场地没有这个方向。其实这个就是要想训练，就就是这个关键点是什么？大胆假设，小心求证。五个题目太多了，没做了。我们全做五个，我们来做也不可能。
Report, please.
Okay, hello everyone. My name is Utachi from Team S601. And the topic of my report today is problem number 11, pumping straw. And here is the problem statement. A simple water pump can be made using a straw shaped into a triangle and cut open at the vertices. When such a triangle is partially immersed in the water with one of its vertices and rotated around its vertical axis, the water may flow up through the straw. And we need to investigate how the geometry and other relevant parameters affect the pumping speed. And we will mainly focus on the speed variation of the pumping and the relationship between the rotating speed and the pumping situation. And the right side is our experimental video. We use motor to let the straw can keep rotating. And because the water will pumping out, the water in the container will be pumping out. So the water level in the container will decrease. So the water resistance to the straws will also decrease, and you will let the straws rotating faster. And we can see that if the straw rotating speed becomes faster, and the height of the water pumping out will become higher, and the shape of the pumping out water will more look like a droplet. And here is the pumping system. The first step, the straw will start to rotate. And when the straw is rotating in the water, and the water will also start to rotate. And that is the first motion of the water. And then it will form a secondary flow, and the water will gather to the center of the bottom. And because when the water is close to the center, and the water will form a big pressure under the straw's inlet part. So the inlet part, it will form a higher pressure, and the outlet part, that is the lower pressure. And because along the streamline and the pressure difference, we can use Bernoulli's principle to explain this phenomenon. And because the P plus 1/2 log V squared plus log GH will equal to a constant. So we think that if the pressure gradient become bigger, and the velocity gradient will also become bigger, so the pumping speed will become bigger. And we know that the direction of the water flow, it will move from the higher pressure part to the lower pressure part. So in our experiment, the water moving direction will like the inlet part to the outlet part. And here is the extra observation. The right side video is that when the water level is lower than the straw's inlet part, the straw also can pump out the water. But the process of it is not continuous. The straw, it will rotating without pumping out water at a short time, and then suddenly pump out a little bit water, and then come back to rotating without pumping water. And we think that is because of the ventral effect. The A1 part here, the area of it is bigger, and the A2 part here, the area of it is smaller. So the A2 part, airflow velocity will become faster. And when the airflow velocity becomes faster, it will form a lower pressure. So the water will tending to move to the lower pressure part. And in our experiment, because the straw will keep rotating, so it will disturb this part of the air. It will let the center of the air become higher velocity. So when the airflow velocity becomes higher, and the pressure of it will become smaller. So we think that the water will tending move from the edge to the center. And when the center water volume increase and touch to the straw will pump out the water. And here is the force analysis. We just draw the normal force and the centrifugal force and the dirt. And we assume the water flow as a single ball divide the balls as an observer. So we need to consider the Coriolis force, which is equal to the -2m omega cross v. And the direction of it is into the paper. And because the direction of the water pumping out, we need the first is the FC cosine theta. And if the FC cosine theta, the direction is like this. And if the FC cosine theta is bigger than the FG sine theta, and the water may flow up. And here is our experimental setup. We use variable resistor and connect the power supply and motor to let the pumping straw can keep rotating. And that is our pumping straw. And here is the data when we change the voltage. And we can see that our control variable is the angle of the straw, and the diameter of the straw, and the immersive of the straw. And we control the immersive is the 2.5 centimeters. And we can see the right side picture when the power circular's voltage increase and the initial angular velocity will also increase. And because the direction of the force, this one is equal to the mr omega squared cosine theta. So if the omega become bigger, and the force of it will also become bigger. And we think that the pumping speed will also become bigger. But in our experimental data, we can see that when the voltage increase, angular velocity increase, and the pumping speed will increase. But the 4 milliliters, when we change the volt is 4 volts, that will not is the biggest pumping speed. And we will discuss this phenomenon later. And the left side picture is that we do the experiment of changing the immersed depth of the stroke. And we found that if the immersed depth decrease, and it means that the water resistance get to the if the immersed depth increase, it means that the water resistance to the stroke will increase. The immersed depth increase, water resistance will also increase, and it will let the rotating speed decrease. And we can see that the angular velocity will decrease when the water immersed depth decrease. But in our experiment, because the water will pumping out, so the water level will decrease. And we think that the rotating speed of the stroke will increase. So we also think that the pumping speed will also increase. But in the right side chart, we can see that that is not like our imagination. So I want to explain the data of it. The first part, we can see that when the voltage increases, the maximum of the pumping out amount will also increase. But the 4.5 volts, it was smaller than the 4 volts, because we think that is because when the voltage of it is 4.5 volts, it will rotating speed is too fast, and that the water pumping out situation is not continuous. The shape of the water will look like a droplet. It's not continuous, so that the pumping speed becomes slower. Okay, and this part we can found that when the volt of the power circulars increase, and the time that reach the maximum of the water pumping out amount, it will decrease. Because if the volt of the power circulars increase, and it means that the stroke's rotating speed increase. So if the stroke's rotating speed increase, and that will from the secondary flow faster. So if the secondary flow from faster, and the maximum of the amount of the water, the time of it will faster. Okay, and this part we can find that it will a little bit up and down, and we think that is because of the Venturi effect we talked about. Okay, and here is the parameter we change the stroke theta angle, and this part is the stroke theta angle. And from the right side picture, we can see that if the stroke theta angle become bigger, and the initial angular velocity will decrease. We think that is because we control these two sides of the stroke. So if our angle become bigger, and the immersed area of the stroke in the water will also become bigger, and the water resistance will become bigger, and you will let the rotating speed become smaller. And when the rotating speed becomes smaller, we think that the pumping speed will become smaller. So in our data, we can see that when the angle increase, water resistance also increase, the angular velocity decrease, the pumping speed will decrease. But it will just happen in the 30 degrees to the 45 degrees. And when the pumping speed, when the 30 degrees and the 35 degrees, the pumping speed will bigger than the 25 degrees. And we want to discuss about that. And from the chart, we can see that when the angle increases, the maximum of the pumping out amount will increase. But the 25 degree was smaller than the 30 degrees and 35 degrees. We think that is because the 25 degrees shows that because it's more vertical to the ground, so it will have more gravity components. So it will let the pumping speed become smaller. Yes, and here this part we can see that the angle increase, the time that reach to the maximum of the water pumping out will increase. And that is because when the angle increase, the rotating speed decrease, and the secondary flow, it will form slower, so we will like the chart. And this part is the ventral effect. We said that when the water level is lower than the strokes in the chart, it can also pump out the water, but it is not continuous. And here is when we change the stroke pipe diameter. And we can find that the right side picture is that when the diameter increase and the angular velocity will decrease because of the water resistance will increase by the diameter is bigger. And we can find that in this 5 picture, we can see that in the 4 milliliters to 8 milliliters, the water will fully fill the pipe of the stroke. So we think that maybe the 4 milliliters cannot pump out the water immediately. And the 12 milliliters that it will just have half of the area of the pipe. So we think that it cannot be efficiency and be limited by their by its rotating speed. And so the conclusion of the data is that when the water resistance increase and the angular velocity decrease, and the pumping speed will decrease, and that just happened in the 12 milliliters because the 4 milliliters to the 8 milliliters, that's the pipe is too small and the stroke cannot be, the pump out water cannot be immediately pumped out, and the 8 milliliter has the best pumping efficiency. And so that is the conclusion. Secondary flow causes the inlet part and outlet part have pressure gradients, and the Bernoulli's principle causes the pressure gradient that the water flow out through the straw and pump out. And ventral effect that can explain why the straw also can pump the water out and when the
question of opponent.
Okay, thank you.
So how do you ask, so your V in is equal to V out, your water go inside the pipe, the velocity the water go inside the pipe and the velocity go out.
I think that will not be the same.
Will not be the same?
Yeah.
Okay. How do you calculate the velocity?
You mean the water
Came
flow
out.
came out velocity?
Okay.
No, we didn't calculate it.
Okay. What is the main force? So turn to the page 8. So it's as you say, there is another force that is air pressure, the Bernoulli's force that it goes up.
We said that because the water will tending to move to the lower pressure part, so the moving direction
The
is
Bernoulli's law.
yeah. Okay.
So you also mentioned jack force is the inside the pipe there was a force that resistance.
It means the friction of the water.
No, it's not a friction of the water. Next question. Do you think that the water level is important?
Yes, I think the water level is important.
Okay. Is that the water in the pipe is laminar flow? It's stable.
I think if the rotating speed become faster and it will not unstable. It will not stable.
It will not be stable. Okay. It is your equipment page 9. Page 9. Do you think the stick is stable? It will not shake.
If
Time is up.
Okay. Thank you.
opponent, please.
I'm Jerry and fellow competitor. I'm Angel from Jinchen High School, and I'm the opponent for the problem statement 11 pumping school. This is the problem statement. A simple water pipe out can be made using a straw shape into a triangle and cut open at the vertex. When such a triangle is partially immersed into water with one of the vertices of rotate around the vertical axis, water may flow out through the straw. Investigate the geometry and relevant parameter and how to affect the pumping speed. So the parameter that affect the pumping velocity is the main focus. This is the reporter structure. For the observation video, they talk about the rotation and the pumping. So for the theory model, they talk about the Bernoulli's principle and the virtual effects, and also the jack force, I think the air resistance, also the centrifugal force and the gravity. For the setup, they use power supply and motor. For experiments, they use the angular velocity, diameter of the straw, and the angle of the straw. For the conclusion, they also talk about the relation of the parameter and the data. This is the strong point of the reporter. The first one is the clear demonstration of the quantitative explanation of the phenomenon. Also, they have a good analysis of the theoretical model. Also, the derivation explained. For the weak points, the comparison between the theoretical models and experiments, but they got good time management. This is some time to be discussed. For experiment setup, the moment inertia of the rod is not uniform. Also, they might not control the stick that's the pumping stick is in the center. Also, the theory, we need to discuss the force analysis, also the jack force in water, as I said, also the viscosity. For the experimentation and the fitting of the data, also the experimental derivation and the boundary of their experiments. So, that's
All three.
discussion. Okay, we can use the blackboard.
Yeah.
First of all, I want to check that you said that it is not the laminar flow, it's a turbulence, right?
You mean what condition?
In the pipe, the water in the pipe is turbulence flow, unstable.
No. I said that if the rotating speed becomes faster and the flow of it, if the rotating speed is slower and the flow of it is the shape of it will like a column, and I think that is stable. But if the rotating speed becomes faster and the shape of the water will like drop it, and I think that is not a stable water flow in the stroke. So it has a limit when the rotating speed becomes faster.
You mean that it might be the laminar flow, but if it over the limits, it will become the turbulence in the pipe.
Yes.
Okay, but do you know that the Bernoulli's laws need to be used in the laminar flow?
I know. So in our theory part, we said that this is the stroke, and yeah, with the water pressure will become different. So the water will be structured. So because in our experiments we all control the both of the power supply is 4 volts except the parameter of the volt. So in this situation, we think that is the steady water flow in the stroke. So we think that it can be used the Bernoulli's principle to explain this one.
Okay. What is the limits? You say that if over the limits, the water in the pipe will become a turbulence. What do you think the limit is?
I think because how we change in our parameter we change the 4.5 volt, right? The volt of the power supply. In our data, we can see that if the 4.5 volts is we use the 4.5 volt, and we can see that the point of it, the pumping speed of it is lower than the 4 volt. And I think that is because the non-continuous pumping situation. So I think the limit of it is bigger than the 4 volts.
So in your use 4.4. So up to the 4, your limit is 4.
Yeah.
But the 4.5 is also used in Bernoulli's law.
I think that
the force.
I think that cannot fully use the Bernoulli's flow, and because we also use the secondary flow, it means that when the water is rotating, and because this part it will keep rotating, so you will get the water velocity in here is smaller, so the water in the edge will want to move to the center, and so it will that this part will have a bigger pressure, and that the pressure of the water become bigger will can move to the lower pressure.
So you mean in this the force will be like this, or I mean
that is also because it has the pressure.
I mean the 4.1 and 4 the drag force there is sorry this one the pipe the stall, and this one the force is like centrifugal and then one and the Bernoulli's. And this one
We also use the components of the centrifugal force like omega squared capacity.
But in this one, it will be another one goes up, and another one goes up, and then also the air pressure, and the centrifugal force. They're gonna be 4, and this is gonna be 3 force.
No, I mean that this is not the force. I mean it's the when this row is keep rotating, right, and will disturb the water in the center, and the water flow velocity in the center will become faster, and so the pressure of it will become smaller. So the container A water
The pressure will
but it will
smaller, so the water will push
yes, it will
center.
move
So
to the
they're also gonna be there a force.
but it will happen in every situation in our experiment. So every
Sorry. Why the reason why I'm talking about the 4.5 and the 4 is because that you said that at the over the 4 there will be turbulence, so you cannot use the Bernoulli's force. So you don't have this one.
So if that cannot be used the Bernoulli's force, and we think that can be used the components of the centrifugal
So
force.
in this diagram, you compare these two one, but their force is different.
All of it will have a component of the centrifugal force, but because this is stable, so I think that it can be used.
I mean, there's gonna no this one, this
So the velocity of it will decrease. It was smaller than the 4 volts. It will faster than the 4.5 volts because that can be used in the Bernoulli's transformer. The 4 volts that is more stable, so that can be used in the Bernoulli's transformer. But the 4.5 volts is not stable. It's because you said
not stable, so you cannot use the
yes, but all of them will have the nr omega squared capacity. And because that is unstable, so if the speed of counting of it will be smaller than the 4 volts, and the 4 volts electricity.
You mean they both have this one?
Yes.
But and also both have this one.
Yes. This is the component of the system.
Okay, I'm not quite agree with that. Okay, the next one. We just talked about the jack force, the air resistance in the pipe, which is there's a jack force, right?
Yes.
You mean which is that's the water level importance.
Yes, the water level.
Okay. In my opinion, that's the jack. This is the pipe, but I mean.
I know.
There's a jack force.
Oh, yes.
So how do you calculate it?
You mean the rotating speed or what?
You mean the water in the pipe might be have a resistor, right?
The water in the pipe will have a yes.
Yeah. How do you calculate it?
We didn't calculate it, and because I didn't put it on the macro. But I think that it should be considered.
That should be considered. I can give you a suggestion that you can calculate the jack force might be this also might be considered. So that's okay. Or do you make sure I understand it right or not? You say that the V in won't equal to V out.
Yes, I think the big won't equal to be out if we want to use the Bernoulli's principle. These two are not the same.
Can you like experience set up the water level? I want to ask is stable or not?
You mean that state?
Yeah, the state.
I think that if the state length is become bigger and it will unstable. But I think that
in my opinion, maybe you get that something that control it to up and down, so it will not shaking.
oh
Maybe you can do it in the future. And how do you measure the time per second the amount of water you calculate? How do you measure it?
because the water pumping out, the water level will also decrease, right? If the because the water will pumping out, so the water level will be decreased.
Yes.
So we calculate the decrease of the length of the water level decrease, and then for every 10 seconds. So that is the decline of our pumping speed.
You mean the water level will go down? Okay. Sorry. So your flow rate is unstable because your water level goes down.
So we use the 10 seconds. And because if the scroll is rotating and the water is rotating, maybe you'll like this.
I'm not sure that I understand it, but this is material. So as we mentioned, there might be a drag force. Do you agree with that?
You said that
This is the drag force.
that is
This one.
Okay. And then the friction of the water.
No, it's not the friction of the water. It's when you move, and this.
Time is up. Summarize, please.
Okay. I have discussed with the reporter about the water level is important or not to the experiments, and he mentioned that it is important. Also, we have talked about the most important one is Bernoulli's theory can be better used in this situation. In my opinion, I think that it might be the turbulence, so it could not use the Bernoulli's, but the reporter thinks that there is another force too that can be used in that, which is I'm not disagree about that. Also, he didn't consider the drag force of the water, which is the opponent think that it is important. I think that's all.
Question or review?
Okay, so for you both, do you think the density of the water impacts the law?
Density of the water?
Of the liquid inside? It will change the density of.
Oh, I think that will affect the result.
Yes.
How about, do you think the viscosity of the liquid will impact your law?
What?
Viscosity.
Is possible.
Is that your liquid will stick on your surface?
It might affect the experiments.
What do you think about how it will affect?
You mean that the water sucks?
Yes, how it will affect.
Like the capillary force?
No,
I think it is, yes. The water, the viscosity between the water and the straw's wall, and that will let the pumping speed become slower. But if the rotating speed becomes faster, I said that the shape of the droplet, shape of the water will become like a droplet. I think that is because the viscosity force is too small to let the water shape like the water color.
Okay, I think the velocity will drop down.
Oh, okay. And how about, do you think the length of the straw impacts the law?
I think it will make the velocity drop down.
You mean the length of
Length of the straw, like your straw is like this here.
Yes, I think that will affect the result.
How about the temperature? Do you think the temperature will impact?
In general, I don't think that it will affect the velocity of the water, but I think it would, maybe I could consider it in the future, but it didn't affect a lot.
Okay.
I also think that will not affect a lot.
How about the vortex caused by the spinning? If you spin, there will be vortex in the middle of it. Is
If
that?
the immersed depth become bigger, and I think it can observe so it will have a vortex. But in our experiment, because we control it is 2.5 centimeters up, so we didn't found that will form a vortex.
How about you?
Okay,
Do you think the vortex caused by the spinning will affect your experiment result? Vortex is when your straw is spinning and there is water spinning on it. Yes, it is.
yes.
Okay. For the water, how can you make sure your straw pump rotates in the center?
Rotate in the center because we stick it to we use motor and that is on the motor.
Yes.
So I think that is always in the center of the computer.
Okay, thank you. And what do you think is the most important parameter that influences your experiment result? The most important parameter that.
I think it's the angle of the spark.
Okay. How about you?
It's the amount of the water.
Okay, thank you. I'm the reviewer from the team, and so for the overview of the reporter's presentation, she used by Bernoulli's principle and the Venturi effect to calculate. And the setup, she used power supporter and motor to control her experiment. And the conclusion is that she find out the relation between the angular velocity and pumping speed, and also the diameter of the straws that will impact the pumping speed. And so for the reporter, the pros are she explained the condition clear and had comprehensive graph. However, the cons are she didn't analyze the data clearly and it didn't draw the friction force in the water. And also, some of the chart are lack of error bar. And for the opponent, I think she explained the phenomenon clearly. She explained the phenomenon clearly and has great understanding on the Bernoulli's principle. And however, for the cons, I think the friction of the water can be more considered about. And for the discussion, the opponent asked, "Do you think the water level is important?" And the reporter answered, "Yes, it should be considered." And we think we are agree with the reporter. And the opponent asked, "Is the water in the pipe stable?" Reporter answered, "If the speed is faster, it will be more unstable." And we are also agree with the reporter. However, the opponent asked, "Can the Bernoulli principle be used?" Reporter answered, "It can be used." However, we think as the velocity become faster, the Bernoulli principle should not be used. And also we asked, "What do you think the main factor is?" And the opponent answered, "The amount of the water." And the reporter answered, "The angle of the straw." And we think it's the angular velocity of the straw. And also, we asked, "Do you think the length of the straw affects the result?" The opponent and the reporter both answered it will become faster. And we are agree with it. And also, we asked, "Do you think the vortex caused by the rotating speed impact the result?" The opponent answered, "Yes." However, the reporter answered, the angular velocity isn't too big, so the vortex is light enough to be neglected. And we are both agree with the opponent and the reporter. We think as the vortex isn't too big, it could be neglected. However, as the angular velocity increase, it should be considered. Thank you, everyone.
Conclusion, please.
Okay, and here is the concluding remarks. Thanks to the opponent and reviewer gave some useful suggestions in my report. I have some typo on the page 7. It should be like when the voltage increase, the time that reaches the maximum of the water pumping out the mouth will decrease because of the secondary flow. And in my report, I have in the structure we make sure that our state is stable enough. It is enough short so that the straw can rotate stably. So we control the stable of the rotating of the straw. And in the discussion, secondary flow cause the pressure of the bottom of the straw will become bigger, and we can use Bernoulli's principle to explain the experimental result about the condition that in the 4 volts. But because the 4.5 volts is unstable, maybe cannot use the Bernoulli's principle that. But we think that also can use the centrifugal force component force to explain why it will pump out the water. And the opponent considered that the drag force, but I didn't consider it. Therefore, I think maybe we don't need to consider it because we should consider viscosity to explain why the shape of the water will become like a droplet in the rotating space become faster. And we also need to consider the water resistance. And the vortex is not, the vortex is not considered in our experimental result because we control the immersed gas, which it will not form a vortex obviously. And I want to say that the conclusion of my experimental result, when the voltage increase, the pumping speed will increase except the 4.54 because the shape of the water will look like a droplet. It is not continuous. And when the angle increase, decrease, pumping speed will increase except 25 degrees because the gravity component.
And this question of the equation.
Can I clarify something? So when your voltage, the control voltage is increased from 4 to 4.5,
Yes.
then your pumping speed increase or decrease?
Then it will decrease.
Increase, okay. Thank you.
Another question.
What if you turn this triangle upside down, and what would you observe? What would be the results? Different.
You mean that if the angle is like
So turn the triangle upside down.
this one?
Yeah.
I think that because
Did you do
it
the experiment?
I think that maybe the water will not pump out.
So it's a guess.
We didn't do the experiment, but I think that the pumping speed of the water will decrease significantly.
I agree with the reviewer because the centrifugal force will be decreased, and also the water in the container will not will immerse in the center, not the edge.
Another question.
If we change the shape of the triangle with a wider angle, would the pumping speed change?
I think if this angle becomes bigger and the immersed volume of the straw will also become bigger in the water. So the water resistance, maybe, I think the water resistance will become bigger. So it will affect the rotating speed of the straw. And when the rotating speed of the straw is become bigger, the rotating speed of the straw will become smaller. So I think the pumping speed will also become smaller.
So while the angle will decrease the pumping speed?
When the angle is decreased, I think that the pumping speed will increase when the rotating speed becomes bigger. But if the angle of it is too small and then the gravity component become bigger, and I think that will also affect the pumping speed become slower.
Because you change your angle, so the water level, the pipe that touch the water, the area will be bigger if you change the angle. So the drag force will be, the resistance will be bigger, so also the velocity will decrease.
I agree with the reporters and the
Can I make, because I only asked because I forgot. How do you think? Answer the question I asked. So when they go to the 4 to 4.5, then reporters say the pumping speed increase. Do you agree?
I agree because as the ball go from 4 to 4.5, the pumping speed becomes faster, and the water go inside isn't a stream. Instead, it is a droplet, and that will decrease it.
Depends on the angular velocity, and also there will be. I don't think that the newest scale will be applied in this
So
situation.
the pumping speed will increase when they go to the state.
I think there will be a little bit decrease.
Your experimental finding, when the angle theta decreases, pumping speed increases. I don't quite understand that because when you change this angle, if you have a fixed straw side length, then other things can also change, like the immersion length and also how much length is above the liquid. So are you sure are you sure those things do not matter?
Because in my experiment, I also control. I just control these two sides and change the angle. So and control the immersed height. So I think that if we change the angle of the stroke and that the immersed volume in the water will change. So the water resistance change and the pumping speed will also change.
I a little bit agree with that because you can change the parameter you can change is the radius, the depth. You might change the area that the pipe touch the water, so the drag force will be bigger, so that it will affect the velocity.
I think it will decrease the pumping speed.
Okay, thank you. Marking time. Ball reporter. Seven, six, seven, six, seven. Ball opponent. 6, 6, 6, 5, 7. Ball reviewer. 5, 5, 6, 5, 6. Thank you all for 15 minutes